long story of how Christmas became Christmas that there, but basically the time that Christmas was actually an old Druid holiday where they celebrated the return of the sun, because prior to December 21st, the days kept getting shorter, so the old European Druids, which is an old religion at that time, believed that the sun god was leaving them. And then there was a huge celebration when they would see that the days are starting to get longer again. So Christmas is actually about 4 days after this winter solstice that there. Now in Malaysia, of course, winter solstice, this, you know, the summer solstice, the autumn equinox, the fall equinox, those days don't really mean too much, but if you look at places like Ireland and England and northern, you know, Denmark, you know, Holland, you know, northern Europe, those are huge days in the calendar whenever you're in a four-season country that there. So as Constantine was uniting Christianity in the Roman Empire, he decided to take all the many of the old Druid holidays and convert them to Christian holidays. So Easter happens to be right around the spring equinox, right there, and Christmas is right there at the winter solstice. So that they're not really the original holidays that they're intended to be, but they follow the old Druid holidays, which were pre-Christian. And Christianity, of course, is pre-Islam. There, so it's kind of interesting when you look at these holidays, how they fell into place in the Western calendar. You know, and I'm not saying that one religion is right or wrong in doing that. I'm just saying that, but those holidays were picked not for religious reasons, but as a way of, you know, because everyone got used to celebrating at the Christmas time. There's a huge celebration that there. And Christmas at one time in Europe wasn't like it is today. It was a huge party, drunken orgy, essentially what it was. And actually the English banned it at one point. And the early Americans banned the celebration of Christmas because it was too much of a sinful party time that there. And then later on, Christmas came back as a holiday that was more religious in nature. And now it's just an excuse to shop and buy gifts for people that there. So you don't see it much in Malaysia, but if you go to the United States at Christmas time, it's just sale, 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 buy, buy, buy at there. So, and most stores tend to, you know, they call it Black Friday, which is the day after Thanksgiving, which is another Western holiday. It's about a month before Christmas. And let's see right there. Is this the right slide? Yeah, this is the right set of slides. That there, because that's when the stores finally make money. Most of the year they don't make any money. Then the month before Christmas is when they make about 50% of their profit for the year. That tells you how much people spend on Christmas in Western countries, especially the U.S. The U.S. is probably the worst in that area. So, and I say that being born and raised in the U.S. And, you know, and I watch my son with my, and hopefully he does listen to this video, and my daughter-in-law, and how much money that they spend on the 3 kids. It's just obscene. You know, I love the kids dearly, that there, but the amount of money they spend is just insane. Okay, that there. Okay, what I'm going to talk about today, and I don't want to. Okay, this one's mine. I want to make sure that I separate the ones right there. Is the programmable logic device structures that there. I mentioned many times during the course in all of our labs, we did not use discrete components that there, and that 90% of digital electronics today does not use AND gates, OR gates, flip-flops in their raw form. That they use programmable logic. So we have this whole course that we're teaching really what I consider a legacy type technology. You need to understand it in order to use the current technology, but you're not going to use it very, very much. That there. And what you're going to use if you're going to be doing digital logic is you're going to be using some type of programmable logic device. That there. And we've already seen that in our labs. Matter of fact, one of the discussions we were having at my previous university was this, we still teach the same course. We don't use this book, we use the Floyd book. We have used this book before, but the Floyd's a little, we use that book, so I'm familiar with both books that they're, and how are we going to get components to do the labs? Because we got some hardcore old-time people that still think that people should build digital logic circuits out of 25 gates or out of 25 ICs. And some of these projects, they come in on 3 or 4 of these prototyping boards that are very, very large. When you could do everything that used to take 15 to 25 chips can be done on one chip. So it kind of drives people crazy. But the truth is, why would you want to use 25 chips when you can use one? There. So we're going to go through some of this here today, and there's not much of this on the final exam other than just some definitions there, and we'll kind of hit that there. And I'm not sure if I put that on this final. Unfortunately, I have to go back and look at your final exam before I review for it, so I can know what's on your final, because I've written multiple digital finals over the last 3 months there. So we're not going to get into the data book information too much. We're going to get a little bit into comparing the different programming techniques, looking at the different types of PLDs, some of the architectures, and we're going to look at, in particular, at the Altera devices there. So the Altera devices, yeah, right there. I skipped over that there. This is the big hierarchy, right there. This is everything you wanted to know about digital electronics and what type of devices and what type of families we have right there. As we look at this right here, we've been working in this area here. And is my pen going to work? Right there. We've been working in this area right here, and my pen is not working. Right there. Didn't I just put a new battery the other day in this class? Yeah. Is my Bluetooth turned off? I wonder if, oh, I bet you I turned off my Bluetooth. No, if I turned off my Bluetooth, then my mouse wouldn't be working. So, oh, now it's working. Okay, standard logic. So we've been looking at standard logic. That's what this book spends most of its time talking about right there. So, and that covers TTL, CMOS, ECL. These are different electronic families. And what those are is transistor logic. That's a standard bipolar transistor. CMOS is another type of transistor. And same thing with the ECL. These are different types of transistor families. And if you study this material in detail, I know that the course that our transfer degree students that when I looked at the syllabus from Sheffield that we were supposed to model, they spent a lot of time talking about these different electronic characteristics. I kind of flew over it because I don't consider it important, since you're not going to use these parts anyway. So I don't get into the difference between TTL and CMOS and ECL. It's not that critical for what you're going to see in the real world. Now we get into the other family, which is a broad family called ASICs. Now when we look at ASICs, that's an application-specific integrated circuit. ASIC, right there. Every chip out today started off as an ASIC of one type or another. So if you look at your cell phone, that processor with all the glue logic, everything else, it's an ASIC. It's an application-specific IC. If you got a digital camera, that's an ASIC that drives that particular one. Now, it becomes, a off-the-shelf component when they make enough of it and they sell it as an off-the-shelf component, but almost every chip falls under that there. Under the ASIC family, we got 4 types of devices right here. And in my advanced digital course that I used to teach in the US, I spent probably quite a bit of time going through each of these 4 families right there. A full custom chip is one that you design from scratch all the way down to the gate level, actually all the way down to the transistor level, right there. I mean, you sit down and you figure out how the silicon's going to look that there. Very tedious, takes a long time, very, very densely populated chip, very powerful chip, and very cheap once you make the first 5. Full custom chips are used in a lot of applications where you need the highest performance and the lowest cost. And you're going to make a lot of them, or you absolutely need the performance. You know, I could look at situations, for example, satellite systems, you know, out there, which you're not going to probably do much in satellite systems, but ITT Aerospace, you know, near where I used to live and where we had a number of our faculty consult. I never consulted for ITT. A number of my students would work for them, and I've been to their plant many times in their design center. They build components for satellites. Now, satellites, they don't make a lot of satellites, but they have to be very high performance, very, very tough, rigorous standards that these chips have to meet because they're going out in space. They're in size and space and weight is a huge problem out there. So they will go with full custom. That's one extreme of full custom. Another extreme of full custom is a company such as General Motors, which makes automobiles. They make the Chevrolet that's imported to Malaysia. I don't know if they used to import the Opel, which was a General Motors car. I don't see too many Opels anymore. In the U.S., Buick, Chevrolet, and Oldsmobile and GMC were all General Motors products. They're a big automobile manufacturer. They also make trucks and that there, and they sell millions and millions and millions of cars every year. So they will use a full custom chip simply because they're making millions of these chips. So they want the lowest cost per chip out there. When you deal with a full custom chip, the rule of thumb used to be the first 5 chips cost you about $10,000 US each. The 6th chip costs you about $1.25. So all the upfront money was in what they call non-recurring engineering costs, NRE, non-recurring engineering costs. It was the design costs. You know, that's the engineer sitting behind the computer with the 27-inch monitor, 2 27-inch monitors sitting there laying out what the silicon's supposed to look like out there. So Intel spends a lot of money doing full custom chips. Trust me, with the performance that you get out of a 6th generation i7 processor, that was all done by hand. You know, with a lot of really that there. So that's the full custom. That's the top performance, lowest cost per gate once it's designed, but the upfront cost is huge. The next generation is the standard cell, and the standard cell is somewhat like grabbing, you know, designing with a TTL parts list. In other words, there's a standard cell for an OR gate, there's a standard cell for an AND gate, there's a standard cell for a address encoder, there's a standard cell, and all you do is you hook up these cells up, and you don't design the cells themselves, you just do the configuration for the cells right there. So it's an easier design process. The cost of the full custom and the standard cell to actually manufacture is about the same, because when we manufacture chips, here's a piece of silicon right here. It's actually round, but then they cut it in little squares right there. I think everyone's seen seen them on the movies or whatever but it's a round disc anywhere between 8 inches and 20 inches there. And the way that a silicon IC is made is they take this piece of silicon and they put a mask over it. They put a mask over it, where some of the areas are exposed and some of them are not. Then they'll expose it to a gas right there. And this gas is either positively charged or negatively charged right there. So they'll expose it to something like arsenic or boron or something that's got a valence of 3 or 5. Silicon's got a valence of 4. That's getting into the chemistry and the physics of how a semiconductor works. But silicon is a crystal that has 4 electrons in the conduction band. So it says it's got a valence of 4. If you strip one of those electrons away, it now has a valence of 3 and it's positively charged. You give it an extra electron, then it's going to be negatively charged. So you expose it to a gas to either provide it with extra electrons or take some electrons away. So you create a material that's either positively charged or negatively charged. So you put this mask on. Then you take that mask off and you do another one, and you do another one, and you do another one, however many layers you need to create the circuits you need. So a standard transistor has got some N material, some P material, and some N material right there. That's an NPN transistor. Actually, this is not quite right. This here is way down here. This is very, very thin. This is N, and this is your P material. And this is the emitter, the base, and the collector right there. Actually, it's the other way around. This is the collector, the base, and the emitter right there. So, and you probably, from what I understand, you haven't had your basic electronics course yet, right? Right there. But transistors are made of negatively charged material, positively charged material, and negatively charged material. So you make transistors with this process right there. So going back to our discussion, standard cell and full custom, you have to do all layers of the mask. The manufacturing process is completely custom for any chip you want to make out there. So they're both very expensive in the NRE because the chip manufacturer has to generate a full set of masks there for every new design out there. The difference is the full custom is the masks are designed by hand, where the standard cell, the masks are kind of put together quickly, but they still have to do a full set. And you have to devote the entire process to building just that standard cell or that full custom. A gate array goes back to our earlier discussion of we can do everything we want with nothing but NAND gates or NOR gates. So a gate array is a couple million NAND gates or NOR gates put onto an IC. And then the top layer, which is the interconnect, is then designed right there. And of course, these designs are done mostly by computer when we look at gate arrays. So gate arrays are still relatively expensive because they're customly made chips right there. But they're much cheaper than the standard cell or the full custom right there. Full custom is a very niche market on people who design full custom chips. I have never designed a full custom chips. I've kind of gone through the process. We had a company that built a couple of full customs. Like I said, ITT did a couple. Magnavox used to do a few. When I was working at Magnavox, I knew some people that did a few full custom designs. We didn't do a lot of full custom. Too expensive out there. Delphi, which was in the southern part of the state, near Indianapolis, they were the design center for General Motors. They did a lot of full custom work. I don't think there's anybody in Malaysia that does full custom designs. They do some full custom manufacturing for Texas Instruments and that there, but the design work is not done locally out there. But gate arrays, they do everything but the top layer. You know, it's still a custom chip, but you do everything but the top layer right there. So those are much more common in the commercial market, and even that there. I've done a number of gate arrays over the years. I've never done a standard cell. I've never done a full custom. I have no experience in laying one out and doing the design. I've done multiple gate arrays over the years right there. And actually the gate arrays, most of the time what we do is the design cycle is we do it in a FPGA, which is right here, or a CPLD and VHDL, and then we turn the design over to the company who's going to manufacture the chip, and then they port the design over to to the gate array. So we actually don't design the top layer that there. So the most common today is the PLD market. That is the most common that there, and that is the most likely what you're going to see if you work in the digital world in Malaysia. That there. So that there, and that's broken up into 3 different areas, and one is the small scale, right there, simple PLDs. Under that are very simple designs that there, and they also include EEPROMs, fuse proms, things like that, but they're relatively simple programmable logic devices that they're. And then the largest group, there are the complex PLDs and the field programmable gate arrays. That there, and the boundary line between these is very, very fuzzy. That there, what denotes a CPLD and what denotes an FPGA, right there. So I'm not going to worry so much about this layer down below here because I'm going to stop there. Now, there's another branch that we haven't talked about, and that's the microprocessors and the digital signal processors, right there. And that's what's covered in your next semester course on microprocessors, right there. And this is, again, these are not programmable logic in the sense that we reprogram the chip and change its hardware configuration, but these are systems that are designed to operate finite state machines and execute instructions as you feed them in terms of software. These are all software driven right there. All this is hardware driven. Even though VHDL looks like software to you, the result out of the VHDL compiler is a configuration that sets up the hardware right there. Microprocessors and DSPs are software driven, and they're not part of this course. They're part of, they're part of the microprocessor course, they're part of the microcontroller course. And if there's a DSP course, it will be part of that. The digital signal processor is a special type of microprocessor right there. So an example of it, and you see microprocessors, you've got one in your pocket right here, right there. There's a microprocessor in here. There's a microprocessor in here. There's a microprocessor probably in that there. Microprocessors are probably 60% of the digital electronics out there are some form of microprocessors. That there, others will be using some type of FPGA or CPLD, right there, or gate array if they have a large enough quantity, right there. That's going to be the other side of it, right there. So the microprocessors tend to be that they're. We're not going to talk about this in this class. So basically, the only thing that would show up on the final is just kind of a general idea of this table here, right there. What this table looks like. Minus this bottom level. I don't care about this bottom level. Up there. And just realize that we've got 3 levels here. I don't care so much about this level here either. That I don't care about. Up there. I care about this level here, these 4 here, and I care a little bit about this level here. And the fact you need to know that this exists even though we didn't cover it right there. So we've got 3 branches off the top. So, again, I've already talked about all this, so I'm just going to kind of slide through these here. I have a bad habit of talking to the introduction and out there. So, category DSPs right there, out there. This is a kind of an interesting note there. A hardware solution for digital design is always faster than a software solution. Out there. If speed is important, you almost always go straight to a hardware solution, right there. That's why when, back in my previous lifetime when I was dealing with military electronics types of applications, we used a lot of hardware solutions. If you're doing things such as digital cameras where you're processing a lot of information and you need to process it very quickly, you're almost always going to use a hardware type solution out there. Your phone is a mix. You know, the image processor is going to be a hardware custom. You know, the image processor is going to be a hardware type design out there. So DSPs out there. So out there, and hardware solutions are typically cheaper if the numbers work out right there. They're cheaper and smaller for embedded systems if you're making enough of them right there. You know, that's a big key is right there. So it's what there, whether the easiest to prototype and get working and get out in the market is a software solution. I could come up with one microprocessor design that can, hardware design, that could do 5,000 different applications. All I have to do is change the software in it. Right there. The hardware design stays almost the same. Right there. When you go with a hardware solution, you're changing the hardware with every design, but you don't have any software to contend with. Right there. Which is best? And that is which is best really depends on the application, right there. So, and I'm not going to get into that there. Third category are ASICs. These are ICs designed for a specific application. And then under the ASICs, we got the PLDs. We talked about that there. They're usually the lowest cost of the subcategories. That's not true because the PLD is the lowest cost in terms of design and development, but in terms of implementation, that there, what you have to look at when you look at this, and this is not part of this course, so that there, but it is part of life. That I've got an application. I'm designing some type of system. I don't care what it is. It can be an engine controller for an automobile. It can be the guidance control for a ship. It can be a GPS system for inside of a dash in a car. It can be whatever. There. So it's got certain requirements it needs to meet. If the system happens to be the control module for a washing machine, then those requirements are relatively simple. A washing machine's got 4 or 5 outputs it's got to deal with. It's got the valve to fill the washing machine. It may have 2 valves if it's a Western washing machine where it's got hot, cold water. If it's in Malaysia, it's only going to have the one water temperature. It's going to have a sensor to see what the water level is. It's going to have an output to drive the agitate motor, an output to drive the spin motor, an input to check to see whether the door is open, a keypad for programming it, some type of timer. It's a relatively simple design. There, most washing machine controllers I could probably sit down and probably design in probably a couple hours. And I could fit them easily into a relatively small PLD. Right there, a small Altura chip, nothing like what we've got there. So if we look at the thing, if your system's much larger, but the question comes in is, when we look at cost, we've got 2 costs: NRE, which is the design cost, and prototyping. Right there. Right there. NRE is the cost of building the first model. First one. That's the cost of getting our prototype up and running. That's a one-time cost. One-time cost you pay for that. Then you got the recurring cost. Right there. The recurring cost is a per piece cost. How much does it cost to build each and every one of these? So when we look at all these various technologies, it's almost always a business decision which one you're going to go to. It's not necessarily an engineering decision. The exception would be, as I said, space and military electronics, aerospace. Boeing and Airbus have certain requirements that it doesn't matter what it costs, you have to meet those requirements right there. So, the size of a 747 or a Airbus, whatever the current model of the Airbus out there, I don't follow the Airbus, but I think the newest Boeing is a 787 right now. The Dreamliner is the newest Boeing aircraft. All of its avionics has got to fit into a certain amount of space and weigh a certain weight is all it can have. They have to do certain things. So if they have to go full custom, even though economically it's cheaper to go with FPGAs, they're going to go full custom because they need the requirements that they're. But in most cases, it's an economic decision. Proton says that they expect to sell 3 million of the ISIS, I guess, is the newest Proton out there. We expect to sell 3 million of those over the life of the car. So how much is the per chip cost versus the NRE of going full custom versus FPGA? That there. So that's really when you get into it. Because going back to this slide right here, it says generally the lowest cost in subcategories. That's not true when we get into large quantities. That's true in terms of design costs. And the reason it's true is you can program these on your desk. I mean, you program them in the lab. All it takes is a cable and you just plug it in and you're done there. So PLDs are very, architectures are very diverse and dynamic. I'm not going to get into them in great detail. The simple programmables, the complex programmables, and the FPGAs, they're quite often grouped together in what they call high capacity program logic device. There. As I said, the boundary line between an FPGA and a CPLD is very, very fuzzy. There. So typically in the past, Xilinx made FPGAs, Altera made CPLDs, but now they're both making that there. So gate arrays are logic functions, interconnection that they're a custom mask is stored much like a mask program ROM right there. Where we have the top layer mask. That they're actually FPGAs also can fall under the category of OTP or reprogrammable right there. So less expensive of that they're see again. This goes back to the discussion here we had a few seconds ago here. Generally the lowest cost of the category. Then in the next slide, they contradict each other. That there is individually less expensive than PLDs with a comparable gate count. So what they're saying is the per piece cost is cheaper with a mask gate array than the per piece cost on a programmable device. But the custom programming process is very expensive and requires a great deal of lead time. And that gets back to how many are we going to make? Is it worth it to go to a full gate array or to go with a field programmable part? Right there. And I should point out that this slide is dated 2011, and this slide's probably later than that, but the cost of going to a gate array has gotten cheaper and cheaper over recent years. Right there. I could probably, for about 5,000 US dollars, probably send a design off to LSI or Atmel or one of the other custom houses and get back a set of prototypes within about 10 working days. So it's not nearly as what it was. I remember when the first gate array I worked on was for a company called Carrier, which builds air conditioner systems, and it was for the controller for a large heating, ventilation, AC for a system that there. And it took about a month and a half before we got our prototypes back after we set the design, and it cost us like $30,000-$40,000 for the for that initial prototype. And fortunately, that one worked right the first time. The next one that I wasn't working on it, but I did some work with it, the group. They screwed that one up, and the prototypes came back and didn't work out there. So that's usually a bad thing when the prototypes don't work when you're doing gate arrays. You want to make sure that they work the first time. So standard cell. This uses a series of available cells stored in a database. The design costs for standard cells are higher than mass programmable gate arrays with greater lead time. So when we look at this here, we look at the programming costs, the FPGA and the CPLD, they're down here at 0. We pay nothing to program those. We do the design, we just hook the cable up, the design goes straight to our system. We go to our mass gate array, the cost is here. We go to a standard cell, our cost goes up to here. And we go to a full custom, our cost goes up to here. So as we go this direction, our cost and our time to do the design gets more expensive. But then our per piece cost goes down. So what you're going to find is that if we do one thing, here's our cost of making it right here. If we do another design, we start off, there's our NRE, and our cost is going to be like this right here. We have a break-even point there, where it's cheaper to go with say the mass gate array or the standard cell right there. So cell functions smaller, generally allows for higher speed and get cheaper manufacturing costs. You know, so the first slide said the first one is the cheapest. What the author really meant is the cheapest on the NRE, not the cheaper manufacturing costs. Full custom is the ultimate ASIC source. All components and interconnections are custom designed by the IC designer. It takes man years, if not decades, to design a chip. Right there. Requires significant amount of time and expense, operate at the highest speed, and require the smallest die area, which significantly lowers the manufacturing costs. When we look at something like the original 8086 processor that Intel put out back in the 1970s, for example, or 1980s, early 80s, that thing took about 15 man years to design. Now, it didn't take them 15 years. When I say 15 man years, it took them about a year and a half or so with about 30 designers on it. So, you know, up there. So there are multiple designers, each spending a year or more on the design. There. So when we talk about one engineer working one calendar year, that's 1 man year. There. So when you look at that, in 1 man year, if you're talking designers, it's right around $100,000 US cost. Now it's a little cheaper if you can pull engineers from India or elsewhere. If you're talking US engineers, it's usually about $100,000 per. If you're talking from elsewhere, it might be $70,000. Because you also have to include all the extra costs, not just the engineer's salary, but you're talking all the overhead. So you're talking millions of dollars and probably billions of rates. You know, there. I'm still thinking U.S. dollars in these numbers, but you're talking a huge amount of money to do a design. That's why you have to talk about millions of chips that you're going to manufacture, or a very rich customer that needs that. You know, Boeing is a very rich customer. Airbus is a very rich customer. The U.S. Department of Defense is a very rich customer. They can pay for these very expensive. The Malaysian Air Force is not a rich customer. They will not pay for a custom design. They can't afford it. So they're going to buy what they can get off the shelf and just deal with that type of performance. So this is basically getting to this. I'm not going to, you know, this is an introductory cycle just to kind of give you an idea of what's out there. I'm not going to get into great detail. This basically is a very simple and/or array right here. We've got our OR. These are our various outputs, and what this is doing is this is an AND gate right here that we're looking at. This is a sum of products type thing, and this is our OR gates right there. And we just do our fuse to which terms we want right there. So as you look at some of our designs that we talk about with the Carnot map, where we have, you know, that there we could do this here is 2 inputs. This is all 4 possible inputs right there. If we have 4 inputs, we would have 16 of these AND gates there, right there. And we would have, this is all 4 possibilities, and then we connect whichever terms we want right there. So there's no need to simplify the circuit right there. It's a very simple circuit in terms of that there. So they just show here that we blow a fuse. That's just that there. I've actually worked on designs with PLDs where I sat down and you would pick and choose which fuses you wanted to blow. That there. That's how you would design your circuit right there. So you would say X is equal to, and then you would have this A naught B plus A B right there. So that means that I want to blow all the fuses, but this one I would leave intact, and AB I would leave this one intact. These 2 I would blow in order to get that function right there. So you would just simply blow what fuses you right there. And I'm not going to get into great detail on that there, simply because it's different for every software package how you do that there. But you just simply write your function out in terms of, and you don't simplify it. You just take it right off the truth table. Right there. Just take it right off the truth table. Right there. Proms work very much the same way. That there. I'm not going to. Programmable logic array is very similar. That there. Field programmable gate arrays is again that they're used in state machine. They're not as widely as accepted. I don't disagree with that. FPGAs are programmable FPLAs. Yeah, FPLAs, that's true. I've never used an FPLA. I've never used one. They're not very expected. GALs, I've used GALs that they're. And again, I'm just skipping through these because I don't expect you to remember all these that there. This is the Altera Max family. This is an older family. We're using the Cyclone, but it kind of shows what's going on here. We have a series of what they call LABs, which is a logical array block. Inside that there's usually 16 macro cells in each block. Each macro cell is basically a flip-flop with a lookup table right there. We have our I/O control blocks, and here's our I/O pins right there around the outside. We also have some dedicated clocks right there. I rarely ever get inside the chip and worry about what's going on inside the Altera chip. What goes on inside the chip is really not that important unless you're pushing the edge of the design. We use this chip in our labs out there. We did the one lab with the stoplight last week, or was it last week we did the stoplight? Or the week before? I can't remember. I think it was last week. When we went through and did the stoplight, we wrote the VHDL code. The software converted that over into the logic that went into the macro cells and did the design, the hardware level design for us. So we stay one level above that there. So, I'm skipping through some of these. So we stay one level above. We really don't have to get to the hardware level very often. And I would suspect none of you will probably be in a situation where you have to get inside these chips. You may get in a situation as industry changes, and as I commented before, most of you are in your early 20s, a few of you might be in your late teens. I don't know if anybody's younger than 18 in this room, but we'll say most of you are probably between 18 and 24 out there. It's probably a safe assumption, right? So currently the retirement age in Malaysia is what now, 60? That there? It's hard to think about that when you're 20. You're thinking that I've got a working career ahead of me of 40 years. That there, trust me, it goes fast. I'm approaching 60 next year, so I started working, in my teens. That there, and I went to university later in life, but I've had 30 years in the academic world plus another 5-10 years prior to that in the industrial world. So I've gone through easily a 40-year career out there, and it's gone by very fast. The one thing that has changed drastically is what I did the technology that I worked with 35 years ago is completely different than the technology we're working with today. 35 years ago, there was no VHDL. We did things with Karnoff maps and doing finite state machines and counters by designing Karnoff maps and looking at state next state. Now I just skip over that and I said I don't even bother teaching it because you wouldn't do it. It's in all the books because a lot of people my age feel that everybody needs to know that. You need to know that. Well, no, you don't need to know that because you're not going to use it. And I've been an engineering manager on various projects out there where I've had engineers work for me. And if I caught an engineer working for me sitting there with a state next state and Karnoff maps designing a counter when he could write it in VHDL, I'd probably fire him probably within the next 10 minutes. That there. Probably the first time I would just scold him, but the second time it's like, no. You're not going to spend 3 hours doing something you can do in 20 minutes. That there. So that's why one of the things I try to point out is that what you're going to see 20 years from now or 10 years from now is completely different than what I'm putting on the slides today. This field changes more than any other field in the world. Right there. I don't care what anybody says, mathematics doesn't change. Shawana, I don't know if I pronounce it right, who teaches mathematics, she teaches differential equations, she teaches integration, multiple differentiation. That hasn't changed in 200 years. Right there. That has not changed. Power machinery hasn't changed. Both basic motor equations have been the same for 40 years. That there. Kirchhoff's voltage law hasn't changed in 50 years. That there. Kirchhoff's current law hasn't changed in 50 years. This technology changes daily. So that's why if you're going to enter the world of digital electronics or microprocessors, be prepared to read constantly out there, because especially if you're going to be on the design side of things. If you're going to be in the manufacturing side, it doesn't change quite as often, but it does change considerably. So this particular slide right here is actually about the 7000S family is probably about 10 years old. That there. In any other industry, 10 years would be very current. In the digital electronics era, 10 years ago is ancient history. That there. So you just have to keep that in mind. Is that this book was dated 2011, so that's 4 years old, and I'm already saying that this slide is ancient history, right there. So, but what we've got here, though, is that we've got an I/O control block. This is where the logic is, and inside each of these, and they don't get into what's inside the logic blocks but each macro cell itself looks like an SPLT. A macro cell actually consists of a flip-flop and a lookup table is basically what it consists of right there. So as we look at these particular parts right here, they're saying that EPM 7128, which is what I used to use to teach this many years ago, has 2,500 gates on it, right there. We're now using a Cyclone 2 that's probably got about 200,000 gates. So as we look at that there. So I'm not going to get into the details of that there. Remember the parts that we've got has what, 672 pins on it? That there. So there's a lot of pins on that there. The programming is done via JTAG and a PC parallel port. That's obsolete there. It's now done through the USB port. Right there. Macro cells, if they're not connected, can be used by the compiler for internal logic. I'm not going to worry about all this. Now we're getting more into the details of the chip, and that's not the goal of this lecture. The goal of this lecture is just kind of give you an idea of what's out there. So, right there, tri-state buffer, so that each pin can be tri-stated. controlled by global output out there. This is all your programming can be tri-stated internally, pulled up to avoid word conflicts. Normally you would tri-state that. Remember, I had you go through and set up, device options, all unused pins tri-stated. Macro cells can be used up there again. Macro cell flip-flops can be used to create a DT, JK, or SR flip-flops right there. So again, we can different architectures based on the lookup table up there, and we can put static RAM devices on there. This is the Cyclone series, which is what we're using right there, and that pretty much wraps up this discussion. The takeaway from this discussion really goes back to my very first slide right there that I spent time talking about. And as I go back through here, this is really where it's the only thing that I want to point out is we look at this particular table and we can see our various choices right there. And then the only other thing is I talk a little bit about, I could have stopped this lecture really after going through the 4, the standard cell and the full custom. Really everything up to that everything after that I would consider is more detail that I'm not going to expect you to remember. But up to from here on that little section, those slides, and I'll get these slides posted on Facebook. So those that there. But again, keep in mind that this is a different topic for a different course, right there. So that little branch right there is a different topic for a different course, right there. And I have worked with, I probably worked just as much in this area as I have in this area, right there. This is probably more than 50% of the digital world is microprocessors. And the reason more of it's microprocessors is that microprocessors gives you a lot of flexibility to make changes after the hardware design is done. Because once you design a PC board, you define your pins, you design your logic, you're kind of locked in. If you're dealing with a microprocessor-based system, you can always go back and tweak software. Right there. So, okay, I think, where am I on time? I probably, yeah.
What difference between microprocessor and embedded?
Well, embedded is actually, this whole family falls under the term embedded. Right there. An embedded system can be an ASIC or it can be a microprocessor. It's probably not going to be standard logic, but it could be standard logic. Embedded just basically means that it's some type of digital control that there. So if it's a hardware-based digital control, it's going to be usually some type of FPGA or ASIC or something like that, or it could be a microprocessor or microcontroller based right there. Embedded is just a general category. So when we look at the difference between embedded, we're talking about some type of digital circuit that controls a piece of hardware of some type. So an embedded system is the engine controller in your car. That there. The dashboard on your car. You're controlling a piece of physical hardware in the real world, right there. How you do that, are you going to use a gate array? Are we going to use an FPGA? Are we going to use a PLD? Or are we going to use a microprocessor? That's up to the individual designer and company that produces that circuit right there. So embedded includes both right there. The opposite of embedded is typically they talk about desktop computing. That's the other side of the coin. Now, I don't consider a cell phone an embedded system. I consider a cell phone a desktop computer that fits in your pocket. That there. It sounds strange, but in all honesty, a cell phone today has more power and flexibility in that there than my first IBM PC that I bought in 1984. My first PC that I bought was this big, and I'm saying it's probably about 2 foot by about 1.5 feet deep and about 8 inches tall, and then it had a monitor set on top of it. The monitor was not color at that time because color monitors were too expensive. It was green, or I could push a button to make it amber. So it had 2 colors, actually 3, white, green, or amber, right there. And it was, and you could see the individual dots in the pixel right there. And that cost $3,000 US at the time, and it came with 64K of RAM. It had no hard drive. Everything had to go through floppy drives on it right there. So, you know, now you're looking at, I don't know about your cell phone, I've got one here, I've got a 64 gig micro SD card in there that I walk around with my entire music collection sitting in it that there. I'm a music fanatic that there. I grew up in the 1960s and 70s in the U.S. during the hippie days, and yes, I had long hair and wore tie-dyes out there, if you can believe that out there. But but you know, I got 64 gig of music, you know, in a phone, and I can put up to 128 gig on this particular phone out there. My first 1 gig hard drive I bought was working on a project for the Navy, and I didn't buy it myself. The Navy bought it. It was $30,000, and we're talking U.S. dollars. And it was the size of a washing machine. And this was in 1981, 82. Out there, it was literally about this tall. I mean, we're talking about 2.5 feet, 3 foot tall, about 3 feet wide, about 2.5 feet wide. Weighed about probably 120 kg, something like that. It was very heavy out there. You know, I mean, extremely expensive, extremely that there. And now you're putting that on the size of something the size of your, you know, something 64 times, 128 times that size, something the size of your fingernail. So remember what I said earlier today, that the digital world changes faster than any other world. Right there, and that goes back to that whole discussion that there. So that's why I consider the cell phone a computer system, not an embedded system. A petrol pump is an embedded system. A heart pacemaker is an embedded system. An EKG machine is an embedded system. Embedded systems are usually dedicated for 1 or 2 applications. Depending on your toaster might be an embedded microprocessor controlled system. Some toasters have microprocessor controls. Some ovens, I've seen toaster ovens. Some ovens I know have digital timers and digital programmable functions. A microwave oven is an embedded system. So the embedded is a huge family, right there, huge family. And any of these could go into an embedded system. It counts anything that there. So I don't answer your question. Any other questions? You know, I mean, we have the final review for the final, and that's the last you see of me until if you end up lucky enough or unlucky, depending on your viewpoint, to see me in another class out there. So, out there. Hopefully, I know this is not everyone's favorite subject, but it's probably more liked than what I hear the microprocessor courses liked. I hear all kinds of stories that students here hate the microprocessor course. That they're, I think it's better now because I put labs into it. You know, and I'm trying to put more labs in the microprocessor course right there. When I got here in January, I asked them what type of lab equipment they had. They said, none, we just do simulations. And I just kind of sat back and pulled out my debit card and got online and bought a bunch of lab components that there. So I bought a bunch of 8051 lab or development boards, and then fortunately they reimbursed me for them, but I was going to buy them anyway because I just felt that they were needed there. So the microprocessor class does include labs, but it also requires writing software. So that's the difference. In this class, we don't write any software. But in the microprocessor course, it's almost about 50% software out there. Okay, disregard that. Where are we at time? Oh, I did the full hour. I'm sorry, anybody who watches these tapes are going to turn around and say, well, you know, you're supposed to have 2-hour lectures. But I tried back in January doing 2-hour lectures, and I found everybody was sound asleep after about an hour and 10 minutes at there. I mean, it just doesn't work at there. And actually, because I don't start recording right away, so it's probably been about an hour and 10, an hour and 15 minutes at there.